Nearly 66 million years ago, an asteroid crashed into Earth and caused a mass extinction. For the first time, an international team of scientists, including 2 from Penn State, was granted the opportunity to collect samples from the peak ring of the remnant crater. This is the story of their journey to the center of an apocalyptic disaster zone.
Scientists hypothesize that an asteroid several miles wide struck the Yucatan Peninsula, sending Earth into a nuclear winter and helping to acidify the oceans, a combination that wiped out 3/4 of the planet's species. Understanding the recovery of species after catastrophic events is a big area of ongoing research, one that Dr. Tim Braylauer of Penn State's Geosciences Department has a lot of experience in.
Geologically speaking, we can only look at thousands of years. If we're lucky, we could get hundreds of years, but that's very, very difficult. So most of the time we're looking at thousands of years. And this impact, the events took place over hours or days, weeks, maybe months, but probably not years. And so we have a real problem there in that the effects were so rapid, but we can only, in the geological record, look at things that took place over millennia. I work on the geological record of phytoplankton, and they have a beautiful fossil record that extends back 250 million years.
Phytoplankton, which are plant-like organisms, are responsible for the majority of the transfer of carbon dioxide from the atmosphere to the ocean, and they are the foundation of the aquatic food web.
They're very important because they are at the bottom of the food chain. So if you impact phytoplankton, then you change things all the way up the food chain. So you go from the phytoplankton to zooplankton to the higher level zooplankton, including things like copepods, to small fish to large fish. And so there's no doubt about it that when you have a mass extinction or a massive change in the phytoplankton population, you have major perturbation to your food chain. So I've been working on the mass extinction for a long time, and we've been working on this event in the deep sea as well as in continental sections where the burial depth is much less.
He was also involved in writing the proposal for the drilling leg of this mission and advised the drilling group as well. When the project was approved, Braylauer put his name in a hat as a volunteer to sail and was chosen. He had never been on a rig before, only drill ships, which were spacious, quiet, and more homelike.
So it's very different. This was much more crowded. There were 6 people in a cabin, 12-hour shifts. The labs were very small. The rig was very small. It was quite different. My shift was noon to midnight, and so I had the other person who was doing the same things as I was looking at the fossil record. He was looking at a different group. He was midnight to noon. So there was always somebody on shift who would be able to provide an age for the cores that were coming up, because we started coring at about 48 or 49 million years. And then we were drilling down through the formations down to the 65 million year horizon. So we had to continuously tell the other scientists where we were in the section.
The expertise that Braylauer could provide was very valuable during the coring process, which, as you can imagine, is a very delicate process, one that relies on accuracy and completion.
Well, so the first thing that you really want to look for when you're coring is getting complete core, complete recovery. So if you drill through 10 meters a section, you want to recover 10 meters of rock. And from that point of view, this leg was extremely successful. Over the course of the leg, I think the recovery was above 99%. So the coring was just tremendously successful, which full credit goes to the people who were in charge of that. The drillers did a remarkable job. So we have a really complete record of this, what happened at the site, which was right at ground zero. So the goal of the leg was to drill right inside the crater, what we'll call the peak ring, which is an uplifted part of the crater, uplifted during the impact process. So much energy involved that granite from deep within the Earth's crust rose up in the crater to very, very shallow depths.
And once again, another success of this mission was the fact that it was a first.
It was the first time that anybody had drilled this close into the peak, the ground zero. So other times people had drilled in the outer rings of the Chicxulub crater on land. But this is the first time that we had drilled inside the peak ring or at the peak ring in the ocean. So we're about 25 miles off the coast.
With the drilling and sampling done, attention now turns back to the phytoplankton fossils. Their distribution patterns through the sediment cores will hopefully help researchers better understand the recovery after this massive impact.
So the goal is to see what happened in terms of the phytoplankton, how did the phytoplankton respond at this place where the environment was perturbed much more than elsewhere, because we have beautiful records of the perturbation in the phytoplankton in places like North Africa and the Pacific Ocean, the South Atlantic Ocean, far further afield from the crater itself. But the question is, how long did it take life to come back right there in the middle of the crater? What we're interested in is, were there long-term effects at ground zero after the impact? For example, hydrothermal circulation. There's a hypothesis that the energy was so great that you started a lot of hydrothermal circulation, and temperatures within the crater rose to 350 degrees centigrade or so. And that would have definitely had a major effect on how long it took life to recover in that place.
As analysis continues, answers will soon surface from 66 million year-old sediments that came from 2,500 feet below the sea floor. For Weather World, I'm Ben Reppert.